Well, this is the last lesson for this chapter. Woohoo! You're going to find that the chapters are just going to process through a lot more quickly. We'll be faster at cycling through the material. So, yay! Tomorrow we're going to do a lab in our face-to-face class, and the test will be on Thursday. So plan on letting me know when sometime this week or early next week you're going to get the test taken. It's just a one-day test. You can get it done all at once. Again, I'd prefer you to come in to take it if you can. Just let me know when you think you can do that. All right, you'll see on the top I have several different places listed. And what you're going to be doing today, you're going to go through that list, and without Googling anything, without trying it first, I want you just to tell me in order from the fastest to the slowest, which environment will melt my ice the fastest. Could be the same size ice, that you're going to want to try to keep as standard as possible. And for this one, it's going to be room temperature, so 70 degrees-ish. Same thing with room temperature here. At least in the school, it's going to be 70 degrees. Whatever your house ambient temperature is, that's what you'll think of for this. Of course, this is 212 degrees. This is all in Fahrenheit. I'm going to guess this is going to be somewhere between 50 and 60 degrees Fahrenheit, 450 degree oven, and a microwave on high. All right, so you're going to make your guess, 1 through 6, 1 being the one that melts the fastest. And you're just going to rank them for me, and you're going to tell me why you put them in the order that you did. I'm not really concerned about that you got that part of it right before the experiment. I want you to tell me, what is your gut feeling about this? Wrong is not wrong for this. It's just, what are you thinking? When you think of that environment, why do you think it's going to happen the way that it is? And then we'll do the experiment tomorrow. You'll do it at home, and then you can compare the actual answers to your answers, and we can discuss what you need to do from there. All right, so the last thing we need to talk about is thermal expansion. And that's a natural consequence. We actually already hit on it earlier in the chapter, but that's a natural consequence of things heating up. As they heat up, they expand. That's the thermometric property. Materials expand at a constant rate as they are heated. Because the rate is constant, it's predictable and useful. And in fact, you use that all the time when you use an alcohol or a mercury thermometer. Based on that, they can calibrate it, and for every degree Celsius, degree Fahrenheit, the temperature goes up, it's going to expand that far into the tube. So there's some relationships about this expansion that I want you to think through. What two things are going to cause more change in length? There are two factors that cause a change in length that we're going to be concerned with, besides the material itself, which is also a factor that we'll talk about. But just generically, any material is going to expand more or less dependent on these two factors. So I want you to take a break. That's my dog just shivering over there. I want you to take a break, go get yourself a glass of milk, an apple, a banana, some grapes, whatever. And while you're getting all that, I want you to think about the two factors of thermal expansion. And when you come back, we'll talk about it. Okay, so whatever fun snack you have, enjoy the fun snack while we work through what the factors are. I hope you were able to come up with two of them, and even hopefully that they're the right ones. It seems obvious that temperature is going to be one of them. And as temperature increases, so does length. He's getting feisty over here. So does length. The other factor is the original length. As the original length increases, so does the change in length. Okay, and I'm guessing that you know intuitively that those are direct proportionalities. As one increases, the other does. We've already said that, and because it's a direct proportionality, I can write it this way. My change in length is directly proportional, that's my alpha symbol, to the change in temperature. My change in length is also directly proportional to the original length. I can overlap those. We've talked about that before. Delta L, the change in length is directly proportional to both the original length and the change in temperature. You can convert a proportionality into an equality by the inclusion of a constant. I am sorry about the shadows. I'm working at my dining room table and it's an overhead light, so the shadows are there. Hopefully you can see it okay and it's not too distracting. So I can convert a proportionality into an equality by the inclusion of a constant. Now this one is very unfortunate. The constant is actually the alpha symbol. So it's delta L is equal to alpha L delta T. This does not mean proportionality. That is the symbol for the constant, and it is dependent on the material as well, and it's going to be specific for that material, and you have a chart that will tell you what the alpha is for each one of those. All right, so we have an example to do with this. Let's go ahead and I need to pull it up. Give me just a second. Let's go ahead and work through the example. We are on 9.10. A steel beam in a bridge extends 25 meters across a small stream. What is the change in length from summer at 38 degrees Celsius to winter when it is a negative 20 degrees Celsius? So I'm going to just go ahead and put down what I know. I know that T naught is 38 degrees Celsius, and you'll know from your chart that it's based on degrees Celsius, so that's good. T final is a negative 20 degrees Celsius, and L to start with is 25 meters. All right, so let's go ahead and throw this into my equation. Delta L is equal to alpha L delta T, or it is going to be equal to the alpha for steel, or the coefficient of thermal expansion is what it's called. Coefficient of thermal linear expansion is 12 times 10 to the negative 6 degrees Celsius to the negative 1. And hopefully you are remembering from math that when something is raised to the negative 1 power, it actually just means that it's in the denominator. So it would actually be 1 over degrees Celsius. I'm already in meters, and I want my answer to be in meters in the end. So that's built into the equation, so I'm good. But I also have degrees Celsius that I don't want to be a part of my answer, so I have to get rid of it. So if there's degrees Celsius in the numerator, I'm going to need degrees Celsius in the denominator in order to get rid of it. So my delta, yeah, that's the unit for it, is delta C to the negative 1. And I should have put this down here, I'm sorry. Alpha is equal to 12 times 10 to the negative 6 degrees Celsius to the negative 1, because I'm not going to put that into my equation. And this is going to be final minus initial, so it is negative 20 minus 38, or plus a negative 38. So my change in length is going to be a negative 0.0174 meters. And all that means is that in this case it has shrunk rather than expanded. If I'd gone from winter to summer, then it would have been a positive number, but it's comparing summer to winter, where my original one is summer. So that's why it's backwards. By the way, that would be a negative 1.74 centimeters. All right, now the same thing, and actually jump down here. I'd like to do another one. Let's look at 11.11 or 9.11. I want to check to make sure that you can see this okay. So we're going to come back to volumetric expansion. But way at the bottom here, and I don't know if you can see how far I am from the bottom, you'll need about this much space for the 9.11. So let's go ahead and get started on that. This is still linear expansion, the one that I'm showing you. I just didn't save myself room for it at the bottom, or under number 3. So I'll just do it down here. So we'll do 9.11. And 9.11 says, give me just a second here. Yeah, you can see this okay. Awesome. All right, 9.11 says, the aluminum lid of a jar of dill pickles is stuck to the jar. To loosen the lid so it can be opened, hot water is poured over the lid, causing it to expand. If the temperature increase of the lid and the jar is 40 degrees Celsius, calculate the change in circumference of the lid and of the glass on which it is screwed. The diameter of the lid before heating is 22 centimeters. All right, so we're really going to need to do, let's just go ahead right now and just do the lid. It's going to be delta T is equal to 40 degrees Celsius. My original length is 0.22 meters, and alpha for the lid is 25 times 10 to the negative 6, and I want to know what's the new L. That's the diameter, so I'm going to look that up. So alpha L is equal to, I'm going to figure that out when I find the circumference. I'm working ahead in my mind, I'm sorry. Delta L, or alpha L delta T. Let's start again. I am going to be looking for my length, and after I find my length, which is the diameter, I'm going to find my circumference. My formula is delta L is equal to alpha L, delta T. Delta L is what I'm looking for, so it's 25 times 10 to the 6 times 0.22 times 40, which is equal to 2.2 times 10 to the negative 4th meters, or 0.22 millimeters. Okay, so notice that this is 0.22 millimeters. It is not the same as what I started with. This is in meters, so it did in fact change. So my new, it's going to increase its circumference by the increase in the diameter. So C is equal to pi d, which is equal to pi times 0.22, and I need to check to make sure that you can still see this. Give me a second. Yep, you can, good. Times 0.22, so my change in circumference is 0.69 millimeters. Okay, so obviously running hot water over it makes it expand. I'm not going to take the time now to do what the expansion would be for glass. You would just use the glass for alpha. You would find that it does not expand as much, and for every little bit more that it expands, that's going to increase the lid of the jar. More than it does the glass, it's going to increase the lid of the jar. And so you'll be able to pop it off. All right, then I just want to talk to you very briefly. It's the same idea. I just want to talk to you briefly about what it looks like for volumetric. Volumetric expansion is going to have the formula, and I should not have written it right here. The formula is going to be, instead of delta L, it's delta V is equal to gamma V delta T. Delta V is equal to gamma V delta T, and it's the exact same thing. It's dependent on the change in temperature. It's dependent on the original volume. So Bunsen burner heats air in a 250 cubic centimeter cylinder, raising the temperature by 20 degrees Celsius. If a movable piston allows the volume to change, then calculate the new volume of the air that's in the cylinder. Okay, so I'm going to write down what I know and what I don't know. V is equal to 250 milliliters. And by the way, the units don't matter for the volume or the length. It doesn't matter, because what you have at the start, you have at the end. And you'll notice that your constants are based on degrees Celsius to the negative 1. So your volume and your length are not unit specific for these, and very rarely do I tell you that, but these are not unit specific. You can use whatever unit they give you, and you don't have to convert. If they gave you centimeters for the length, or if they gave you kilometers for the length, you could use them, because what you put in is what your change in length or change in volume will be. So 250 milliliters or cubic centimeters, we're good with that. Gamma for the cylinder is just given to you in this case. Again, you can get it from the sheet. Is 3670 times 10 to the negative 6, and again it's degrees Celsius to the negative 1, and the change in temperature is 20 degrees Celsius. So delta V is equal to gamma V delta T, which is equal to 3,670 times 10 to the negative 6 times 250 milliliters times my change in temperature, which is 20. When you do all the math, you find that delta V is equal to 18 milliliters. That's actually quite a big expansion. It's asking you the new volume of air. It's not asking you by how much does the volume change. Make sure you're paying attention to how the question is worded. They're not saying what is delta V. They're saying what's the new volume of air. So my new volume of air is going to equal my original volume V naught plus delta V. So it's going to be 250 milliliters plus 18 milliliters, which gives me my 268 milliliters. All right, the homework for this is going to be 41 through 49. 41 through 40. I'm going to switch that. I'm going to do the same thing again. I'm going to double check what I want. That seems like a lot, so I'm probably going to pull some of those out and just pick a couple of them. I know I want to do 46, and I know I want to do 49. For 49, it's about gasoline that's in a drum, and so the volume of the gasoline is going to be the volume of the drum. And so what you're going to do is find out what happens when you heat the system. They're asking how much gasoline do you lose. Don't just identify how much the volume of the gasoline changes, because the volume of the drum is going to change as well. So you have to keep that in mind as you're working all this through. So let me just give you a hint about that one. All right, I'll post on PowerSchool what the homework is. Don't forget you also have the precursor to the lab where you're just going to kind of predict what's going on for this. All right, let me know if you need anything. I apologize that I've not been timely about getting on Zoom. I actually am of a mind that you are attending to the class when you do the homework and when you reach out to me to let me know that you're having troubles. I'm going to ask Mr. Lullman if I can get permission to count that as your attendance. It seems redundant to me to have you show up. As long as you are willing to tell me, Mrs. Warren, I'm really struggling with this. Can we find a time to Zoom together? In which case, I would love to. I would absolutely love to do that. So just let me know if you need me for now. I am not going to worry about Zoom times for tomorrow. If you don't want to bother jumping on and you just want to get to this, I'm okay with it. I'll let you know on Tuesday if I get a chance to talk to Mr. Lullman. All right, take care. Let me know what you need.